Everyone, welcome back to our channel. Today we are going to discuss about very important concept for both AP and TS board exams. That concept name is the Rayoptics. In this we are going to discuss about short answer questions, maybe based on the choice is increased in Telangana state. So we are expecting 2 short answers from this topic. So here first short answer is prism answer. The question is derive the expression for angle of incidence, then angle of deviation, then you can give the expression for the refractive index of the material of the prism. So this is a very important for practical exam also. Look here. Practically I have given this explanation one more video, and if you want you can watch that one also. Look. First we are taking one prism. This is the prism. And we are taking 3 faces A, B, C. This is the normal to the surface. We can consider N1. And this is another normal to the surface. We can consider N2. Look. 2 normals we have drawn. One is on AB, another one is the AC. Then if there is no prism, light is having which path? Straight line path. Without bending it is moving. Light is having the straight line path. Always you know that the angle between the incident ray and normal ray is called the angle of incidence I1. Now whenever we are placing the prism, look here, light is traveling from air to denser medium. Here this is the air, rarer medium, and prism is making with almost we are using that glass for that. So this is the denser medium and this is the rarer medium. So the light is bending. See, if there is no prism, light is going like that straight line path. Whenever the light is passing from air to denser medium, it is bending towards the normal. Look here, this is the normal and it is the bending towards the normal. Now you look here, the angle between normal and refracted ray is called the angle of refraction. It is represented by R1. It is represented by R1. Then you look here. Here the light is coming from denser to rarer medium. It is bending away from the normal. This is we can consider as an angle of emergence I2. And here also we can observe the refraction from denser medium to rarer medium, that is the R2. And we can consider this is the angle N. See here also, if there is no prism, light is having the straight line path like this. This is called the angle of deviation. Look here, this is the angle of deviation. How to define this one? It is angle between incident ray and the emergent ray is called the angle of deviation. Look here, total angle is how much? I1. One part is the R1. So this part is how much? I am writing here. We can take it I1 minus R1. And here also how much it is? I2 minus R2. I2 minus R2. Look here. From prism or from, you can give, this is the M. Angle of the prism is A. And this is the Q, this point, and this is the R. From quadrilateral, A, Q, N, R. We can write it A plus N is equals to 180 degrees. From this we can write it N equals to 180 minus A also. Here A is the angle of the prism and this is represented, this here the angle is represented by N. And from triangle, next case, from triangle, look, QNR. What we are writing? R1 plus this N plus R2, 180 degrees. But already you know that instead of N what we are writing? R1 plus 180 minus angle of the prism I am taking A only plus R2 equals to 180 degrees. When 180 degrees is going that side, it will be cancelled. So directly I am writing, when A is going that side, it becomes to plus. So A equals to R1 plus R2. This is equation number 1. It is the expression for angle of the prism. So based on that refractions, we can find out the angle of the prism. A equals to R1 plus R2. We can take this is equation number 1. Then we can focus on angle of deviation. Look here. Angle of minimum deviation is represented by delta. This formula is sum of the deviations, nothing but I1 minus R1 plus I2 minus R2. So deviation of this light is the sum of the deviations. One is the I1 minus R1 plus I2 minus R2. Then how to write this expression? Here delta is the angle of minimum deviation. Delta equals to, we can write it I1 plus I2 minus is the common R1 plus R2. But already we know that instead of R1 plus R2, we can write the angle of the prism. So delta equals to I1 plus I2 minus angle of the prism. Then I1 plus I2 equals to, we are getting delta plus A. See, for minimum deviation, we should consider for minimum deviation, we can take it I1 equals to I2 equals to I, and refractions R1 equals to R2 equals to R. Then how to write this expression now? I plus I, look here. I plus I is equals to delta plus A. Then I equals to how much? Delta plus A by 2. This is very important expression. We can take it. This is expression number 2. Then for minimum deviation, we can change this one because R1 equals to R2. So we should write from here to here. R1, R plus R equals to A. From this, R equals to A by 2. So we derive the expression for angle of the prism, then angle of the incidence, and angle of the refraction. So based on that, we can write the expression for the refractive index of material of the prism. What is the refractive index of the material of the prism? See, there are many formulas, but here we are using the Snell's law. Refractive index equals to sin I by sin R. I means not this I, that is the angle of incidence. Here I equals to delta plus A by 2. Then refraction is how much? A by 2. So mu equals to, we are writing sin I by sin R. Then instead of I, we are writing sin A plus delta by 2 divided by sin A by 2. Sin A by 2. So this is the expression for the refractive index of the material of the prism, and we can write here mu equals to, final expression is sin A plus delta by 2 divided by sin A by 2. So this is about the prism. Look here, first we have to trace out the prism. If there is no prism, light is having the straight line path. Whenever we are placing the prism, light is bending, angle of refraction is R1. Here angle of refraction is R2. Angle of incidence is I1. Angle of incidence is I2. Then we can go for quadrilateral AQANR. We can write it angle of the prism plus n equals to 180 degrees from this n, that one. Then from the triangle QNR. So R1 plus R2 plus angle of n is equals to 180 degrees. When we are substituting in this, we are getting the expression for the angle of the prism. A equals to R1 plus R2. Then our next thing is angle of minimum deviation is the sum of the deviations. Where we should observe the deviations? When light is coming from rearer to the denser, the deviation is I1 minus R1. When the light is coming from denser to the rearer, that angle of deviation is I2 minus R2. After simplification, we are getting the expression for angle of incidence. We are getting the expression for angle of refraction. So from these equation 2 and 3, we can able to find out the refractive index of the material of the prism. What he said, not Snell's law, that is called the Snell's law. It is the ratio of sine of the angle of incidence. Look here, sine of the angle of incidence. So instead of I, we are writing A plus delta by 2. Then sine of the angle of refraction, that is represented by sin A by 2. Finally, this is the expression for refractive index of material of the prism, sin A plus delta by 2 divided by sin A by 2. Look here, our second short answer question is to define the focal length and prove that f equals to r by 2. First of all, here what is the f? F is the focal length. First we should give the what is the definition for that. See, here we are taking concave mirror. Always you remember that the distance between optic center, see here O is the optic center and the focal point is called the focal length. We are taking, this is the small f, or f also we are taking. This is the f. And here center of the curvature, the distance between C and optic center is the radius of the curvature, you can take it r. See, when the light rays are parallel to the principal axis, see this is the principal axis. Here incident ray is parallel to this one, means after reflection from the mirror, it is passing through the focal point of that mirror. That's why it is passing through the focal point of this one. Look here. This is the incident ray. This is the incident ray. If you want, once again I am drawing. See, this is the principal axis. This is the optic center. So, the distance between optic center and this focal point is called the focal length. It is represented by f. Whenever the light rays are parallel to the principal axis, see this is the incident ray, and after reflection what happens? These are passing through the focal point. If we are considering this is the angle is theta, then if the light is coming from the normal, means it must be passing through the center of the curvature. The distance from here to here, it is represented by r. If it is 2 theta, means half of this one, means this is the theta. Don't confuse. One is the focal point, another one is the center of curvature. Here the distance is represented by f, and from here optic center to C, the distance is the r. R is called the radius of the curvature. Now we want to derive the expression for what is the relation between focal length and radius of the curvature. See, look at the diagram. We are taking from triangle F and D. From the triangle F and D. Tan 2 theta is how much? Opposite by adjacent. Opposite is the ND and adjacent is the FD. Instead of FD, see these are approximately same only, we are taking this focal length. If theta is small, we can write it instead of tan 2 theta, 2 theta. 2 theta equals to ND by F. Then one more triangle is there, from triangle C and D. Tan theta is how much? Opposite is same ND, but adjacent is the radius of curvature r. Same here also, if theta is small, instead of theta we are taking tan theta, we are taking theta equals to ND by r. This is equation number 1. This is equation number 2. Look here. Here you know that 2 theta equals to ND by f. And you know the expression for theta is also ND by r. Now, equation 2, substitute in equation 1. What we are getting? See, 2 into, instead of theta we are writing ND by r. And here ND by f, which is cancelled, ND cancel. Then you are getting the expression for f equals to how much? Do the cross multiplication, f equals to r by 2. This is the relation between focal length and radius of curvature. The only you should remember that figure. Focal length and this one principal axis angle is the 2 theta. When the light is normal, means it will make half of that 1 theta. From the figure we are writing the expressions for tan 2 theta and tan theta. When theta is very small, instead of tan theta we should consider only 2 theta, opposite by adjacent. Here also opposite by adjacent. Then equation 2 substitute in equation 1. Finally you are getting the expression for focal length f equals to r by 2. Then our third question is only concept is there. Look here. Here also we are taking one mirror. You know that as usual this is the principal axis. It is passing through the optic center. Now we are placing one mobile here. This image of the mobile is not longitudinal uniform. Why? What is the reason? Look here. When light falls on this, if it is parallel to this one, it is passing through the focal length. Here when we are taking point object, we are getting clear image. See, look here, we should consider 1 point like that. Whenever that object distance is increases, image distance is decreases. That's why all point sources, when we are looking that image, it is not uniform. That too magnifying power minus V by U. So this is the reason we can't observe the uniform image when we are placing the mobile phone is here. Suppose you should consider here object distance is less, then image distance is far like that. Whenever that object distance is increases, what happens? Image distance is decreases. That's why that mobile phone, it is not looking uniform. Then explain the Cartesian sign convention for the mirrors. It is also very easy answer. Look here. In 10th class also you are having. See, this is the mirror and this is the principal axis and this is the optic center O. If we are measuring the distances from the optic center, but we are taking the sign convention based on the incident ray. See, if we are measuring the distances along the incident ray, we should consider as a positive, and opposite to the incident ray, those we should consider negative. Suppose object is here. When light falls on this, like this, then what happens here? We are measuring, this is the object distance. Generally from where we should measure this object distance? From the optic center to here, but we are measuring opposite to the incident rays, no? So in this case object distance, what we are taking? Negative. Suppose image is same side, we can measure opposite to the incident ray, that is also negative. Suppose image is that side, we should measure from optic center to image, but it is positive. Why? We are measuring along the direction of the incident rays. So like that we should take it. And one more thing, if we are measuring the height of that object, height of that image, and finding the magnifying power, if it is above the principal axis, we should consider those are the positive, and below the principal axis we can consider those are the negative. Like that we should, just you remember that when we are measuring the distances opposite to the incident rays, those are negative. It may be focal length, it may be object distance, or it may be image distance. Like that, heights, when we are going through the heights or any value above the principal axis, we should consider as a positive, and below the principal axis we should consider as a negative. Our fifth short answer question is define critical angle and explain total internal reflection. First of all, what is the critical angle? When light travels from denser medium to rarer medium. Suppose we are taking air and glass. Which is the denser medium? Glass is the denser medium and air is the rarer medium. Like that, when we are taking water and air also, water is the denser medium and air is the rarer medium. So in this case, when we are defining the critical angle, we must remember that light travels from denser medium to the rarer medium. For particular angle of incidence, the angle of refraction is 90 degrees. That angle of incidence is called the critical angle. Look here. We are taking different diagrams. Look. This is the surface. It is separating. This is the rarer medium and this is the denser medium. It is normal to the surface. Look here. When light coming from denser to rarer, this is the angle of incidence. And this is the normal to the surface. Here light is bending like this. We can't call this angle of incidence, is called the critical angle. Then second diagram, look here. Same thing, this is the normal, but here I1 and this is the I2. I2. Angle of incidence is how much in this case? I2. See, here also this is not calling angle of critical angle. Then third diagram, look here. See, this is the normal. Same, light is coming from denser to the rarer medium. Here we should consider angle of incidence is how much? I3. Now you look here, light is grazing on the surface, and how much angle of refraction is there? This is the 90 degrees. We can't call this is critical angle. I1 is not critical angle. I2 is also not critical angle. But now I am writing I3 is a critical angle. Why? For this angle of incidence only, the respective angle of refraction is how much? 90 degrees. That's why I3 is called the critical angle. In this case, angle of refraction is not 90 degrees. But third case only, for particular angle of incidence, critical angle is how much? 90 degrees. So you can say this particular angle of incidence is called the critical angle. This is about the critical angle. And what is the relation between critical angle and refractive index? We can write it mu equals to 1 by sin c. This is the relation. Now we want to explain that total internal reflection. What is the total internal reflection? From this only we should explain this one. Look here. This is the surface. Here also light is coming from denser medium to the rarer medium, like that. Here, if the angle of incidence is greater than critical angle, now you look here, angle of incidence is greater than critical angle. See, light is coming back into the same medium. Light is coming back into the same medium. This is called the total internal reflection. Got the clarity? See, if angle of incidence is equals to, see when angle of refraction is 90 degrees. But in this case, angle of incidence is greater than critical angle, means the light is not going into the rarer medium. It comes back into the same medium. This is called the total internal reflection. Practically in the case of optical fiber also, we are sending the waves. So in that case what happens? No need of writing this one. This is the application. Here core is there and clad is there. See, look here. When light is incident here, this is the normal. Here angle of incidence is I. Then it is refracting. Look here. Here angle of incidence is greater than critical angle. Light is coming and is incident. Here also angle of incidence is greater than critical angle. See, it is going like that. Wave is traveling into the pipe to inside the optical fiber without any loss. Look here, it is not going to the other medium. This is the one of the application of total internal reflection. Now come to next question. This is very important for final exam expected for final exam also. Then our sixth S.A.Q. is the explain formation of a mirage. See, this is completely like our imagination, and in our daily life also we should observe that one. In hot summer we are going for long trip. We are driving that car. Long distance we feel on that road water is there. When we are going there, there is no water. That is due to the mirage. And one more thing, when we are standing nearer to the pool and when we are looking inside the pool, what happens? We can observe that long tree is there. Look, this is the pool and this is the tree. When we are looking down, what happens? We feel that the tree is inside the pool. That is our feeling only. Practically it's not possible, and that concept is called what? Mirage. Mirage is the application of total internal reflection. During the hot summer, that temperatures are increasing nearer to the earth. What happens? The air becomes hot. Whenever the hot air is having the less refractive index, when tall objects, not small objects, when tall objects like tree, pole and that one, no, when light rays are coming on this, these are bending away from the normal. Immediately we can observe that their angle of incidence is greater than critical angle. So we can observe that total internal reflection. Because of the total internal reflection, we feel that under the pool one tree is there. Like that we should observe the mirage. So this is the application of mirage, total internal reflection. Now our seventh question is, why sun appears red during the sunset and sunrise? You know that when the light is coming from sun to earth, that rays are having the different colors with GR only. When these are traveling from through the dust particles, clouds are there, that clouds are having the water droplets. So which color is having the more scattering? Blue color is having the more scattering power and red is having the less scattering. So which color is having the more wavelength? Red is having the more wavelength. It is not having that much bending nature. So when light falls on the dust particles, then whatever that atmospheric particles and clouds, what happens? That blue and other colors are participating in the scattering process, but red is not participating in that. That's why during the sunset and sunrise we are away from the sun. So which color we can able to look that one? Only red color. Why? Red is only reached to that one, because remaining is participating, that scattering is more, but that red is having the less scattering power. And one more thing, according to Rayleigh's expression, that intensity of light ray is inversely proportional to the wavelength. So during the sunset and sunrise we can. Next short answer question is the formation of rainbow. It's very interesting concept, and after rain only we should observe that one. Always we should observe this is opposite to the sun and behind of that observer, and this we should observe after rain. And we should remember that rainbow is the combined effect of dispersion, refraction and total internal reflection. What is the dispersion? Splitting of the colors. We can observe the here during the rainbow. And refraction means the rays are traveling from one medium to the another medium, propagating from one medium to the another medium. Total internal reflection means, so if the angle of incidence is greater than critical angle, you know that previous question, how the total internal reflection happens in the case of light rays. See, during rainbow is the combined effect of dispersion, refraction and total internal reflection. And how it is possible? Look here. When the light falls on the water drops, we should observe the rainbow. But there are two types of rainbows. One is the primary rainbow, another one is the secondary rainbow. Look at both sides. This is the secondary rainbow. Sunlight is coming like this. Look here, how many refractions are there? This is the one refraction. Light is coming from air to denser medium, water drop. Here one refraction and one total internal reflection. Here total internal reflection. This is the first time total internal reflection, 2 times of the total internal reflection and 2 times of the refractions. Look here, once again the light is coming back into the air. So this is the secondary rainbow. In secondary rainbow we should observe that 2 internal reflections and 2 refractions. This is called the secondary rainbow. Like that primary rainbow, what happens? Same sunlight is coming like this. Look here. This is refraction and this is the total internal reflection and this is the refraction. Here one total internal reflection is there and 2 refractions are there. This is called the primary rainbow. And here we can observe this. This is the red and this is the violet. See, in this case in secondary rainbow, this is the red and this is the violet. Reverse order we should observe in the case of primary and secondary rainbow. Look here, now we are going to discuss about simple microscope. Based on this, there are 2 questions, and 9th one and 10th one. For both the answers, you can give the common explanation. Look here, first, what is the simple microscope? See, for simple microscope, we are using one convex lens. And what is the role of this one? It is increasing the magnifying power. See, small organs, small particles, everything we can able to see that clearly. Even in botany experiments, we are taking thin layer of that plant. Inside also we can able to see the structure of that one. Everything it is possible with the help of the microscope. Where the journey was started with the help of the simple microscope, and it is increasing the magnifying power. We are using one convex lens as usual. This is optic center. The line which is passing through the optic center is called what? Principal axis. Now where we are placing that object? We are placing the object in between the optic center and focal length. See, this is the object. This is the object distance. It is represented by u. The distance between this optic center, and focus this where AB is the object, that is called the object distance. And where we should observe this image now, A dash, B dash is representing the image. Here the angle subtended by the object is considered as a alpha, and the angle subtended by the image we should consider as a beta. From this, how to find out the magnifying power? See, it is increasing the magnification, means we can find out the magnifying power. Angle subtended by the image at I to the angle subtended by the object is called the magnifying power. When tan is very small, we should write it beta by alpha. In first condition, we can consider that image is formed at near point, means image distance is nothing but near point. What is the near point? Look here. Suppose we want to read any one book, we should maintain the proper distance. If you are placing like this, we can't able to read that one. We should maintain some near point where for human eye this is the 25 centimeters. Minimum we should maintain the 25 centimeters, then only we can able to read. And for far points it is infinity. Suppose one long pole is there, Charminar is there, then Golconda is there, everything we can able to see. While for human eye, far point is the infinity, but near point is the 25 centimeters. Here we can go through the two conditions. Suppose if the image is formed at near point, from the lens formula we are taking 1 by f equals to 1 by v plus 1 by u. F is the focal length, v is the image distance, and u is the object distance. But in the case of convex lens, in this case that image distance is in near point, that to negative. When we are substituting, we are getting that magnifying power is the 1 plus d by f. Look here, instead of v I have written d here. Then d is taking as a LCM, and we are sending this side d by f. Here minus 1, d cancel, and here d by u. Then we want d by u equals to how much? D by u is nothing but magnifying power. So m equals to d by u equals to 1 plus d by f. This is the magnifying power when the image is formed at near point. Then second case, if the image is at far point, just now I have given Charminar and Golconda. At that time, what is the magnifying power of this one? See, here instead of v we are taking infinity, then m equals to we are getting d by f. This is about the simple microscope. Thank you everyone. Please subscribe my channel.